All right, you guys in period 7, you're going to be working on a sheet involving a set of scenarios, and in those scenarios, they actually kind of match the scenarios that we did on that free body diagram sheet. Well, now we're going to try to attach numbers to things, and then also try to solve for various unknowns. So let me give you just a few example problems to kind of give you I guess, a blueprint as to how we want to approach just about every single problem in this unit here. All right, so we'll start off with something incredibly simple. All right, if you have an object that is at rest, we'll call it a 5 kilogram object. We've been saying consistently there's got to be a force of gravity acting on it. In addition to that, there's got to be a normal force acting on this. And we've been constantly saying, well, this cancels out this, but we've never really explained why. So this thing's at rest, and A is 0. And what we know is that if we have the force of gravity, we can always calculate the numerical value of that force. If we know the mass, which would be 5 times 9.81, that's a 49.05 Newton force downwards. And so what we want to do is we want to reason why is that the same thing in terms of its magnitude here. So Newton's second law is sigma F equals ma. And what we can always do is we can just say, all right, here I know that A is 0, which must mean that since A is 0, m times A must be 0, so sigma F must be 0. Basically what that tells us that we have balanced forces. A lot of people go, this is at rest. Why are we applying the second law here? But the second law actually applies to all first law cases. It's just that we're dealing with a case where A is equal to 0. Now what we can do is we can always take our expression for sigma F and we can go, oh, over here, I'm going to actually tell you what sigma F is. It's the sum of all forces. The normal force and the gravity. This, you're going to find that in my free body diagrams, I always label everything as, positive numbers here, but I clearly show the direction of things. This is my opportunity to mathematically represent everything with a numerical sign. So what I'm going to do is say sigma F is the combination of two vectors. The normal force, which is pointed up, and the gravity, which is pointed down. And then just looking at this, I can move Fg over there, and I've just proven that Fg equals the normal force. So the normal force must also be 49.05 newtons. And now I can see why I have a net force of 0. So very simple problem, and then it all makes sense once we start to apply the second law. Now we can do that for a case that's a little bit more complicated. Let's still do an object at rest. Let's take that same 5 kilogram object, tie it to the wall like this. That's not going to keep it at rest. That's a string there. This would just fall back down that way, but here's my ceiling. Let's put a string at an angle of 45 degrees with respect to the ceiling. Now, looking at this diagram, I can identify my forces. I've got two strings here and a force of gravity. So here's my force of gravity. Here's one string, here's another string. I'm going to call this T1. I'm going to call this T2. They're different strings, they have to have different tensions. And what you see is that we've got something at a diagonal, something to the right, something down. Got three forces acting on it, and this thing is at rest. So the acceleration must be 0, and you know what? The net force must be 0. So what we're going to do is take a look at this. I've got things in multiple directions here. We always want to be in components if we have anything at an angle. And there's a little geometry trick here. I would like the angle here with respect to x-axis matches that angle because it's an alternate interior angle. So that angle is 45. And this is my free body diagram right here. It contains my original forces. Your free body diagrams always have to have your original forces. But that doesn't mean we can't modify it to solve a problem. So what I want to do is I want to break that down into components. I can leave T2 alone, that's directly to the right. I can leave Fg alone, that's directly down. But this one would have a component upwards of T1 sine 45. Now I don't even know what T1 is, but I know it would be T1 sine 45. And this would be T2, no, sorry, there's also T1. That kind of looks like a 1, right? Let me write my 1s like that. T1, I'm just going to actually make sure it says T1. Cosine 45. All right, so basically, when you look at the diagram here, you can kind of see why it's at rest. I would imagine that this force and this force balance each other out, and this force balance each other out. And we can actually apply the second law to figure that out. But what we're going to do is, typically the second law is sigma F equals ma. But since we're in components, we're going to do this in components as well. So I'm going to do sigma F in the x direction. And that would equal ma. And again, this is my opportunity to use these two forces and represent them with mathematical sign here. So I'm not going to do these forces because these are not in the x direction. T2 is positive. That's to the right. T1 cosine 45 is negative. And then the other thing is that a equals 0. So let's actually write this as sigma F in the x direction equals 0. And then what we can see pretty quickly is exactly what I said. Move this T1 cosine 45 over to here. I get T1 cosine 45 equals T2. So I know that this and this have to be equal to each other in size. The only problem is I don't know this and I don't know this. Let's look at the vertical direction. Sigma F in the y direction. I could write ma, but this thing isn't moving, so I'll write 0. Again, we're going to use our vertical forces here, T1 sine 45, and the force of gravity. Now, the force of gravity, and when we move it over to here, we say that, okay, it is equal to T1 sine 45. These two things balance here. And now we can calculate T1 because we can also calculate the force of gravity. The force of gravity would be 5 times 9.81, 49.05 equals T1 times sine 45. So I'm going to divide 49.05 by sine 45, and that gives me, nope, I multiplied. Divide, please. A T1 value of 69.367 newtons. Now what I literally did was I calculated T1, not its component, T1, 69.367 newtons. So I actually know what that force is right now. And now we can get T2. We can go back to the x direction. We can put in 69.36 cosine 45 and we'll get T2, which, if I multiply that by cosine 45, I get that T2 equals 49.05 newtons. So now I know my T1, now I know my T2. And if you really want to, you can put T1 sine 45 here, T1 cosine 45 here. You're going to find that they equal this and this, exactly what we calculated. So everything should make conceptual sense to us now running through this problem. Now what I've done is I've applied Newton's second law to two objects that were at rest. Let's have them move instead. So let's take that same 5 kilogram box and let's have it move. Let's have it being dragged to the right with a force of, let's say, we'll say that there's a 15 Newton force of tension to the right. So that will be enough to drag it. And what we'll also say is that the acceleration is 2 meters per second squared to the right. Now that's not the only force in play here, right? You've got a normal force, you've got gravity, and then in addition to that, it's on a surface, so let's say that there's some kinetic friction here. Some people go, what if it's frictionless? Well, if it's frictionless, when we solve for that, we'll get 0. Let's see what we get. So this is a little bit tricky, because this object, if we track its motion, it's moving to the right. It'll be there, then it'll be there, then it'll be there. You may notice that there's no change in vertical position. What that means is that there's no motion in the y direction. So I'm going to expect there to be no acceleration in the y direction. However, there is acceleration in the x direction. So I can say that the net force is equal to 0 because that's 0. But I can't say that the net force in the x direction is equal to 0 because that's not 0. So I can only do it in the y direction. But that being said, let's do it in the y direction. N is up, Fg is down. This is a result that we see over and over again. Move Fg over there, Fg and the normal force are the same magnitude. And you know what, since it's still 5 kilograms, they're both 49.05 newtons. Pretty boring, don't really get much info out of there. Let's look at the force of kinetic friction. That's the x direction. So if I do sigma F in the x direction, our acceleration is 2. We'll write MA. Again, this is our opportunity to write tension, which is positive, and friction, which is negative, because they're to the right and to the left. And now we can put in numbers here. So my mass is 5, my acceleration is 2, my tension is 15, and my force of kinetic friction is unknown. So if I move Fk over there, it'll be positive. Subtract 10 from both sides, I get 15 minus 10. I guess the force of kinetic friction is 5 newtons. So now let's look at our forces here. Basically, our object here has 4 forces acting on it. 49.05 up, 49.05 down. Those two cancel each other out. You got 15 to the right, 5 to the left. These do not cancel out. Basically, we get a net force of 10 that way, 10 newtons to the right. So essentially, when we try to put this in perspective, does it all make conceptual sense? A net force of 10 to the right acting on a 5 kilogram object, when I do the second law, which says net force equals mass times acceleration, if I solved for A, knowing all my forces, I would get 2 here. So it does all make sense. So our approach in every single problem is to identify all the forces, write our free body diagram, and then apply the second law. It doesn't matter if it's accelerating or at rest. However, if it is at rest, at least in that direction, we can set it equal to 0. But if it is accelerating in a particular direction, we have to write our MA because the A is not going to be 0. So there's a taste of how we set things up. That's going to be a universal approach for this unit, and hopefully it allows you to get through just about every problem, and you guys will pretty much, I say, get started on practicing this methodology for the first time.